I was asking that I was asking a question that why do metals conduct electricity? And because the question here they're asking is explain the difference by referring to the structures. That means they're just asking you that what is the difference between electrical conductor and electrical insulator? Okay, so the difference between both of them is this, that conductors, the electron in conductors, electrons are free to move. That means they have delocalized electrons. In metals, they have delocalized electrons. So the electrons are free, they are mobile, they can easily move, they can transfer heat, they can transfer electricity. But the electrons in an electrical insulator are fixed to one place. Did you get those differences, please?
Yes.
Ella,
The
are you there?
metals are have the electron.
Yeah.
So
Okay, okay, good. So, um, electrical conductor, the electrons are delocalized, they are mobile, they are free to move. But in electrical insulators, the electrons are fixed in one place. So that with that, they cannot conduct electricity. So that's the difference between them. And that's 2 marks. Wow, that's good. 2 marks. Okay, now the next question is number 6. Number 6, that's figure 6.1, shows a shower that takes in cold water. The water passes through an electrical water heater and emerges from the shower head at a higher temperature. We have the electrical water heater, the shower head. The power of the heater is 9,000 watts. The shower is powered by a 230-volt electricity supply. Calculate the current in the heater when it is switched on. Okay, now you guys look at this. We have volt, we have watt. So what formula do you think can solve this? Anyone there? What formula? Any idea?
No.
Okay. Carries, any idea? Oh, Carries is muted already. Um, now this,
I so can I
okay.
so I see IR or something. I'm not sure. But
No, no, no. Okay. Remember this formula, P is equals to IV.
hmm,
Always remember this formula. I gave you that W is equals to I square RT. That's when we talked about specific capacity. This is for work done. All right. Now, power is equals to, that's power is P is equals to IV. This is the formula you use. So
Mm-hmm.
I is equals to P over V. So I want you guys to tell me the answer. Solve that and tell me the answer. Yeah, what's the answer, please? Are you with your calculator there?
yes, sir.
Okay.
I'm getting 39.13.
Yes, 39.13 ampere. Do not forget your units. Ampere. Okay. I hope everybody understands that, right?
Yeah.
Yeah.
Okay. Now the next one says suggest a suitable rating for the fuse in the water
Sir,
heater. Yes,
point
please.
one.
You said
Is it
hello.
39.13 ampere?
Yeah, divide it yourself. Whatever thing it gives you, you work with it. We don't need to be fixed to one. Whatever thing it gives you, just work with that. So suggest a suitable rating for the fuse. So we've gotten now what's the essence of a fuse? A fuse is actually used to when large amounts of current coming through a circuit. Now, what will be the rating of the fuse in ampere? What kind of fuse do we use for this kind of circuit? Remember, our current already is 39.1
So
whatever. So
so
suggest a
can we
rating.
use
Okay,
40?
correct. You can use 40. Good. We can use a fuse of 40 ampere. Why?
So that it will not exceed this thing.
Exactly. So that they can be able to carry the amount of current in the heater. Because if we use anything high, we can use 40, we can use 50, we can use 60 ampere. But the goal is that you should use a fuse that is greater than the amount of current it can carry. If not, it will burn.
Mm.
Do you understand that?
Yes, sir.
Okay. The next one is the specific capacity of water is 4,200 joules per kilogram. The initial temperature of the cold water is 16 degrees Celsius. Determine the maximum mass of water that can be heated to a temperature of 35 degrees Celsius in 1.0 seconds. Now, the first thing you should remember is what is the specific capacity of water? Sorry, what is
40.
no, no, no. I was about saying something. Um what is the formula for specific capacity? That's
Q
MC
equals MC delta theta.
MC that consider.
delta theta. Okay. Um we are looking for they've given us specific capacity of water. We have that. The initial temperature of the cold water is 16 degrees Celsius. Determine the maximum that can be heated to a temperature of 35 degree in 1 second. But look at something here. Um, Q. I also told you that Q, based on what we have the power of this, right? We have the power of this heater. Remember, these questions is connected to the next one. That's the previous one,
Yes.
sorry. I also told you that Q is equals to power times time, isn't it?
Yes, sir.
So
PT.
we don't know Q here. So we can just say PT is equals to MC delta theta. Okay, so what is power? What's the power? What's the power? I think the power is 9,000, right?
9,000, yeah.
9,000 times what's the time? 1
1.
second is equals to, we are looking for the mass times 42,200, okay, times delta theta is 35 minus 16, isn't it?
Yeah.
Okay, I need you guys to do that now and tell me the answer for mass. Okay, so when you do that, what will be the answer for the mass now?
I got 0.011.
Are you sure? Are you sure it's 0.011?
That's what I got.
Mm, I'm getting a different one though.
So
Let's,
I have 8.8.
no, it can't be 8.8. It can't be 8.8. Remember, mass will be 9,000. 9,000, not
0.11.
0.11 exactly. That's what I wanted to hear. Caris, are you getting that?
Well, that's not what I'm getting.
Yeah, it is 9,000 divided by 4,000 times 19 now.
It's not 4,200.
4,200 times 19. Come, did you just punch everything in your calculator or you did it one by one?
I'm doing one by one.
This is 9,000 over 4,200 times 19. You can't get 8 point something here. No way. So what are you getting now?
Do the same thing.
Come. Oh yeah, now do this carries. 4,200 times 19.
4,200. Um,
Times 19 is what?
times 79,800.
Now do 9,000 divided by 79,800. It can't give you 8 points now.
Oh,
That means you just punched everything like this on your calculator. That's what you did.
Yeah, I punched everything, but it still gave me the 0.11.
I did 79,800 divided by 9,000.
No, this is simple maths now. We should get this. Okay, now that is it. 0.11 kg. Okay, I hope you guys have written this. I want to clean it off.
Yes, sir.
Yes, sir.
Okay, now the next one is a safety control in the shower switches off the shower when the water becomes dangerously hot. The control uses a thermocouple thermometer to measure the temperature of the heated water. Describe the structure of a thermocouple thermometer. Include a diagram in your answer. Now, there are some things they want to see in a thermocouple. Now, I think I've drawn a thermocouple before for you guys before. Okay, but nevertheless, the things they want to see is number one, there should be two different metal wires joined at one end, and there should be a volt. It can be a voltmeter, it could be a galvanometer. Okay, now this is it. There should be a voltmeter. Um, there could it can be some people draw theirs like some people draw. Now this is one metal wire. This could be steel, or this could be copper wire. This could be iron, and some other ones again. There are different ways they draw uh, a thermocouple. Now there could be, sorry, uh, okay, favor, welcome. Now this is iron. One of this could be a copper, and this could be iron. Okay, iron wire. That's iron rod, copper rod, iron rod, voltmeter, and this is the hot plate, the hot junction, or the junction, hot or cold junction. Okay, so this is it. Now, with this diagram, now some use this diagram, some use this diagram. I think I prefer the second one because it's quite easy and easy to understand. Okay, okay, okay.
So in the first diagram, where is the hot junction? Where is the junction?
Now this they are both fixed at their own junction here. There's a junction here. There's another junction here.
Okay.
Okay. Now so this is it. Okay. Now with this now I suggest one reason why a thermocouple is suitable for this purpose. Why do we use thermocouple? Number one, please write this. It makes measurement fast. Are you writing
So,
this?
but wait, what do we write for the description of the thermocouple
Oh,
thermometer?
the description, I just said that now, that it consists of, I just told you that two different wires joined at one end, a voltmeter is connected. Those are the things you write now.
Okay.
The structure is just to help your diagram. Do you understand?
Okay.
Okay, now We want to look at why do we use a thermocouple for this purpose. Number one, quick response. It makes measurements fast. Quick response. It makes measurement fast. Number two, it measures rapidly varying temperatures. It measures rapidly, sorry, I think this should be here. I'm coming. Okay. Um, coming. Yes. Now, quick response makes measurement fast. Number two, measures rapidly varying temperatures. Measures rapidly varying temperatures. Number three is that it has an electrical output. Number four, it has small heat capacity. And number five is that it is robust and rugged. So as if there's any, it can dictate any slightest change in temperature. Whenever there's a slightest change in temperature, it can dictate it. So that's why we use more of a thermocouple for that purpose. Have you gotten all this, please?
Yes, sir.
Okay, so I can clean it up. It's okay. It's okay. Ah, wow, that was 10 marks. Good. Number seven. Number seven says the resistance of a 1 meter length of resistant wire is 7.6 ohm. The length of this wire is taped to a meter rule. A crocodile clip is connected to one end of the resistant wire exactly at the 0 meter mark of the rule. Figure 7.1 shows the crocodile clip connected to the terminal P. A second terminal is connected to a movable contact using a long length of connecting wire. The movable contact is connected with resistant wire at the length L from the 0 meter mark on the rule. The movable contact is placed at different points of the resistant wire. The resistance R of the L depends on L. Sketch a graph to show how R resistance varies with length for values of L between 0 and 1. Mark the appropriate axis values on the axis of that. Okay. Um, the relationship between resistance and length. The relationship between resistance and length. Now it's something that we need to look at. Okay, and it's asked us to let's see. Okay, the resistance of a wire N 1 meter length. So we would come here and fix here as 1 meter. Oh, sorry. Can okay, 1 meter length. When it's 1 meter, what's the resistance of the wire? Is 7, right? Are you
I'm not
there?
even understand. Yeah.
Okay, this is one,
Is
two.
it not 7.6?
Yeah, 7.6. I want to locate that now.
So, but if you do it like that, will it be that the resistance is reducing or increasing?
That's what we want. That's exactly what we want to find out. So we
Okay.
should find that out ourselves. 4, 6, 8. So 7.6 is somewhere here, right? Mine may not be as straight as that. So if this is 7, for example, if that is my 7.6, I'm coming. Probably my 7.6 should be somewhere here, right?
Yeah.
Okay.
Yes.
So I bring this down. I'm supposed to, remember, I'm not meant to do this. What I should actually do, they said I should mark the points. Where is it? Where is it? They said the question, we should be careful with what they
Mark
said.
appropriate values on the axis of the graph.
Oh, we should mark those points. So I will just mark here. Okay. Now I'm trying to be as detailed as possible. A length of this stab to a meter rule, this exactly at the zero mark of the rule shows the directly connected to P. Um, Sketch a graph. L is zero. Okay. When it is zero, when it was at zero, what is the resistance? Was there any mention of that?
No.
Okay. So that means what we have here, it's a positive gradient. So we have something that moves from here up. We have something that moves up. So that we have something that moves from zero upward. Now we should be careful. Now exactly what they need is this, is that it is marked on top of the, we should have, is marked on top of the y-axis. They need us a straight line of positive gradient from zero to points. That's from zero when it was at zero, and when it was at 1, which is 7.6. That's all they required of us, and that is it. Okay, so the next question is, sorry, did you get that?
Yeah.
Caris, are you there? Caris? Oh,
Yes, sir. Yes, sir.
okay, please don't mute yourself so that we can easily flow. Now, the next one is figure 7.3 shows a battery of electromotive force 12 volts connected across 1.0 meter length of the resistant wire. Explain what is meant by electromotive force. Okay, what is electromotive force? Any idea? Okay, please write this. Electromotive force, this is the work done, or this is the energy transferred. This is the work done, or the energy it takes per unit charge to be transferred around a circuit. This
Drink that
is,
again.
okay, this is the work done, or this is the work done it takes to transfer 1 coulomb per unit charge round a circuit.
So you not say one column before.
Yeah, as you are telling me to say it round, in fact, if you ask me to say it round, I think I'm going to give you something different again. There are different ways of saying that.
1 coulomb of energy around the circuit.
Okay, let's just take a simpler definition also. This is the energy transferred around in a complete circuit. This is the energy transferred, or we can call it the energy per unit charge.
Mm.
The energy transferred around in a complete circuit. Now, what's the difference between potential difference and what's the difference between potential difference and electromotive force? This is it. I would explain this now. Now, the work it takes to transfer energy, to transfer 1 coulomb of electricity, or one coulomb charge of electricity from this point to this point, or from this point to this point, is called potential difference. But the energy or the work done it takes to transfer 1 coulomb of electricity from that point where I started from to this same point again is called electromotive force.
So electromotive force goes round, but
goes
potential
round.
just
Yes,
stays
correct,
place.
correct, correct. It's good. Potential difference is from one point of the circuit to another one point. It could be a short distance from this point to this point. But when it comes to potential electromotive force, it goes round the circuit. So the energy it takes or the work done it takes to transfer 1 coulomb of electricity round a circuit is called electromotive force. Do you understand that
Mr.
now?
Daniel,
Yes, please.
but the formulas for electromotive force and potential difference is the same.
They could be different depending on what you have. For example, potential difference has a formula of I is equals to big R plus small r. Potential difference is also the volts, but they are all measured in volts. So you can still use V is equals to IR.
Okay.
They are still measured in volts. So you can still call them volts because it's still the work done it takes. One is around the circuit, one is just from one point of the circuit to another point of the circuit. Do you understand that now?
Yes, sir.
Okay, so that's
Yes, sir.
electromotive force. All right, now look at this. Calculate the current in the resistance wire. Calculate the current. Oh, calculate the current in the resistance wire. Remember, we have our volts and we have our resistance. Hey, listen, guys. What is the volts here now? The volt is
Well,
what? The volt is 12. What is the resistance? Remember, we are using a resistance. Look at across the 1 meter
So is it
resistance. So
seven
wait,
point six ohm?
exactly 7.6 ohm. You know, they said across the 1.0 meter length. So when it was 1 meter, what was the resistance? The resistance was
Seven point
7.6
six ohm.
ohms, right? So what will be the
Yeah.
current now? What will be the current? The current becomes, you remember using this formula, V is equals to IR. So I is equals to what?
V over R.
Over R. So what is the current? So tell me the current. What's the current?
So I 1.57.
1.6. Okay, 57. That's approximately 1.6. What is the unit? Remember the unit.
Amperes. Amperes.
Ampere. Ella, did you get the same thing? Is Ella here? Okay.
yeah, yeah.
Okay, 1.6 ampere. Correct. Um, it's okay. It's okay. It's okay. Now, they said potential difference. Oh, please, if this thing goes off again, please make sure you come back. Make sure you come back again. Now, the potential difference between terminal P and terminal Q when L is equal to 0.35. Okay, remember now they're talking about uh, potential difference. Now, we actually need to get that from our graph. So if we had a good graph now, we would have done that. Do you understand? Hey, guys, can you hear me? Hello? Hello? Hello?
Yeah.
Yeah, that the next question is from our
Yes.
graph. From our graph, we'll get that. Remember, we got here as 1. Here was
Yes.
1. So they said 0.35. 0.35 will be somewhere here. Remember, we had 2, we had 4, we had 6, and we had 8. So if 0.35 was here, so we just trace it out. So our answer would give us 4 point something. Do you understand that?
Yes.
So that potential, the
But
next
can't you
question,
use can't you use like math to solve it or something?
can't we use what?
Like math.
Maths like
No, no, no,
proportion or
no, no, no,
something.
no, 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 no. It's from the graph because they gave us L is equals to 0.35. So we should be getting something like 4.2 volts. Or sorry, we should be getting something like uh sorry, we should get our resistance. Sorry. We should get our resistance from L, then come back and use V is equals to IR. Then V is equals to, you will know our current already, we know that. And then the R, we find our R. Do you understand
So we
that?
don't need to use the graph.
No, we need to use the graph. The graph gives us the resistance.
Okay.
Remember, the graph
So,
gives us the resistance. We only use the L to get the R.
oh, okay.
Do you
I
understand that?
understand. Yes.
Ella, do you understand?
Yeah.
Okay, now they said calculate the charge that passes through the resistant wire in 5.5. Now, this one you can use math to solve it. Q is equals to what? IT. That's the formula. The charge is now, Q is the charge. We know you know the current, and this your minute, you convert it to what?
Seconds.
You convert it to what?
Seconds.
Yeah, you
Seconds.
convert it to seconds. So we know our I as 1.6, our current as 1.6, and this becomes multiplied by 5.5 multiplied by 60. So what's the answer?
528, I guess.
528. Okay, 528 coulomb. 528 coulomb. That's the answer. Okay. Wow. Now we are entering triangular prism. Triangular prism quickly. Um, Now, triangular prism, figure 8.1 shows a ray of red light incident on one side of a glass prism in air. Now, red light, glass prism. This is a triangular prism. I think, thank God we are saying this. This is what I said. I've not taught you guys. So for red light, the refractive index is NR. The angle of incidence is 53 and the angle of refraction is 30. Calculate the refractive index of R. Yes, I think I've told you guys about this before. So can you tell me how to calculate the refractive index there now?
It's not supposed to be sine I over sine R.
Exactly. That's sine I over sine R over sine R. Sorry, that should be small r, not big R. Okay, so that would be sine 53. Okay, you guys should do it on your calculator quickly. Over sine 30 degrees. So what's the answer, please?
1.5, 1.6.
1.6. Carries, I hope you got the same thing.
Yes.
Okay,
So what's
1.6.
the unit?
There's no unit.
Oh, mad.
There's no unit. So now the next thing is sketch a line to indicate the path of the red light when it emerges from the glass prism. Label this part as R. Label that part as R. Now, now they said sketch a line to indicate the path of the red light. Now, um, the path of the red light, naturally, it should actually, if you are looking at this part, coming, this is like your normal. I'm trying to get, that's where, that's like your, that's like a normal. Okay, but the red light, when it goes into this place, there's a refraction. there's a refraction at this point. I'm coming. Let me bring this. Just give me some minutes. Oh, no. Okay, let's go back this again. Let's do this again. Oh, okay. But this, at this point, now, now, sketch a line to indicate the path of the red light when it emerges from the prism. Now, when it emerges from the prism, the red light refracts the least. Listen, you know the refraction is the bending of rays of light, right? Of light rays, isn't it?
Mm-hmm.
Refraction is the bending of light, isn't it?
Mm-hmm.
So,
Yeah. Now, this is when you see the red light, this is where you start seeing the red light from. This point where it is
so
red. Yes, please.
can you indicate the normal?
Yeah, that's exactly what I just did this to indicate the normal. Okay, showing I just did this to indicate that I wanted to know the parts so that I
I
would not just
thought
know anyone. So now
I
this is
thought
the
the
part. I'm listening to you.
I thought the red light was supposed to go like above the normal. I don't know.
Okay, I didn't even notice this. Now this is it.
Hmm.
I didn't see that. Thank you for even asking that question. Now with this now, this is it. Red light refracts the least. If we had violet, probably they asked for violet light. If they asked for I don't know, is this violet? But if they asked for violet, violet would have refracted at
And
this point.
they asked for violet
Did
too.
they ask for violet?
Yes, in BI.
Where is it? Oh, good, 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 good. Okay. If they ask for violet, violet will refract this way, and red light will refract. Now, violet will refract the most, while red light will refract the least. Remember